My name is Dwayne Dozier. I work for Remy International. I've been with Remy for about 7 years. Prior to that, I owned my own repair facility. We did pretty much everything. As you can see, I still work on a lot of stuff in that shop behind my house. Owned and operated that for about 20 years. Prior to that, I worked in aftermarket parts. Tonight we're going to talk about GM's regulated voltage control. This system is GM's platform for computerized controlled charging systems. The things that we learned tonight, you can put forth to other manufacturers' platforms. There's a little bit of differences. There's some different nuances to them as far as whether they're A circuit or B circuit, which I'll explain in a second, and whether or not they're inverted or just a regular duty cycle signal when we talk about the signaling. So with that, I'll get started. We're going to talk about our heritage. We'll talk about GM's regulated voltage control system, talk about the components of that system. We'll talk about standalone regulated voltage control and how it differs. And that's the one that's going to be in your GM truck line. Talk about that system's operation. And then most importantly to you guys, we'll talk about the system's diagnosis so that you can get these things fixed correctly the first time. So here's some of the things we've done throughout our long history. For one thing, we have a huge OE heritage as far as from 1896 until now. And some of the things we did, like I said earlier, was we came up with the first starters. We came up with battery ignition, alternators with integral regulators. Now this is important in that the fact that we took the regulator and put it inside the alternator. Here's our offerings. We make starters and alternators. Pretty simple, cut and dry. Some of the things you're going to see on the horizon that we'll probably have classes for, start-stop technology. Anybody in here run into any of these cars where you stop beside them and the car shuts off and then it cranks back up as soon as they let off the brake? Well, that was great for gas mileage, but it was kind of a nightmare for us because now we have to go from 60,000 start cycles to 350,000 start cycles. And one of the ways we did that is we increased the brush pack by adding 2 additional brushes. And as far as the clutch drive goes, we added an additional roller and an extra high tensile strength spring for durability. Here's what we do with the alternators. Earlier I said we don't have to go up with voltage because we can go up with amperage, and this is how we've done it. You'll notice that rotor has fans on both sides though. It's because the newer alternators, you notice, will have open casing where there's windows all the way around the unit and on the sides, because it pulls air from the back and the front and it blows it out the side. This is great for heat dissipation and also for debris flow. But these things get to 350 to 400 degrees. So when your customer comes up to you and says, hey, you know, I've got this alternator that every time oil drips on it, it starts to smoke. Yeah, they got a problem there. They need to change the oil leak, right? Fix that oil leak. That's the only problem they have because it will get that hot. One of the things that we've done with the stator to increase that amperage is that we've actually put 2 alternators together. There's 2 stators combined into one. So instead of a 3-phase, we now have a 6-phase stator. Anybody out here remember when in class you do the oscilloscope to see the DC waveform to look for bad diodes? If you had 2 nice DC waveforms and you'd have a flat line, you knew you had a bad positive one, or if it dipped down to the negative, you knew you had a bad negative diode. Well, now it's going to be 6 of those. So it'd be 5 and then a glitch before you'd see a problem. Those thin laminate plates around that stator right there, these are all real thin. They're like a sheet of paper, and they have rectangular squares in them. And for years, we were putting round wire in it. That makes no sense, putting a round wire in a square hole. So we took square wire, 2 pieces of square wire beside each other, makes a rectangular form, so we can completely fill that with copper, and that's one of the ways we're able to get more amperage out of it. More amperage, more power. So that brings us to what we want to talk about. But in order to understand regulated voltage control, we need to understand where it came from and why it came about. This, again, is GM's platform for computerized controlled charging systems. In the beginning, we used to have the 10 SIs. These were the ones that came out, I mean, when they first came out with alternators with internal regulators, this is the one that came out. Completely inefficient for today's cars. Put out like 37 to 63 amps. 1 volt step control, because what it would do is as the power needs increased and that amperage started going up and the voltage started to pull down, the regulator would adjust it by a full volt. So you'd have anywhere from 13.1 to 14.9. No control over heat or resistance output losses. What that means is that heat affects power. When you look at a battery, you look at the cranking amps of the battery. You got cold cranking amps, and then you got cranking amps. And cranking amps is 32 degrees. That's still pretty cold to me. I don't know what you think, but cold cranking amps or cranking amps, you have quite a bit of significant gain from those two. And think about that. From 32, let's say it's 70 degrees, it's almost double that. So the quicker the electrolyte's flowing inside of there from being warm, the more power you have available out of a battery. Well, the opposite's true with an alternator. With an alternator, the hotter it gets, heat induces resistance into copper. So the hotter it gets, the more resistance is there. The more it's working, the hotter it gets, the more resistance there is. It's kind of a runaway effect. So in a case with an alternator, if you were in Oklahoma City and it's 105 degrees, 110 degrees out, which isn't uncommon in the summertime, and you got an alternator like this, more than likely you're running off of the battery when you come to a stop. Because now at idle, you've got less available current. Because the alternator itself does not know how hot it is under the hood, and it cannot adjust for that. So that's something else that this thing didn't do. So at that point in time, they went up in amperage. Still not enough amperage for today's vehicles. A little bit tighter voltage control, but nowhere near like we have today. Today's units, they've put 70 millivolts per step. So it's a real tight voltage control. Still no control over the heat or resistance output losses that I mentioned. And then also with this one, because the other one was only putting out 36 to 63 amps, and we're pushing it around with a big block. I mean, those were the days. You didn't worry about gasoline. We started looking at gasoline, and fuel mileage became an issue. Now the engines are smaller, and this alternator is bigger because more electronic components are on it. So now you've got this heavily loaded alternator that's taking more horsepower to turn, and you've got less horsepower available from the engine. So it caused idle quality problems. You'd come to a stop, and if it was a hot day and the alternator was fully loaded, it would actually cause the idle to stumble. And why do customers bring us cars? Because of their senses. They see something they didn't think was right, they smell something, feel something, or hear something that doesn't seem correct. Well, yeah, if your idle's stumbling, I'm pretty sure that they would bring you the car saying something's wrong here. So GM put out a bulletin at that point in time that said, on a hot day with a heavily loaded alternator, this is an ordinary event for this thing to stumble. Not so much. So the engineering team went to work to fix that, and that's one of the reasons regulated voltage control is around. Cranking loads, this thing, if you had a really low state of charge battery, which by the way, a state of charge on the battery means where's the acid? If the acid's in the water, the state of charge is going to be higher, or in the fluids. If the acid's in the platelets, the state of charge is lower. If you keep cycling it to where it stays in the plates, it's called a sulfated battery because that sulfuric acid stays in the plates, and that's why it smells like a rotten egg when you try to charge it. Well, this thing, if you got a low state of charge on a battery and you go to start it, you've got that alternator almost fully loaded from the start. So now you're pulling that alternator along with trying to pull that engine to start it up. So that's another issue with cranking loads. Again, these things were completely inefficient, so you had terrible fuel mileage. And the first group of these, to try to explain this one, the first group kind of went into this. It's a PLIS system. Now keep in mind that GM uses the same plastic on their regulators for the PLIS and the one that I'm getting ready to show you, the PLFS. So if you ever wonder which one is truly yours on the vehicle that you're working on, is when you look at the wiring schematic, it's going to identify PLIS or PLFS right there on the wiring schematic. So that's an IS. But now, is my unit? One way to do that is to look up that part number or call our tech line, and we'll just tell you. If you look up that part number on RemyAutoparts.com, you'll see that picture of that plug-in, and it'll say PLIS or PLFS, and it'll also explain it. And the one thing that I want to explain about the PLIS is that very few of them used all four of them. P was a phase, which is one leg of the stator, which is AC, a third of the AC power coming out before it gets rectified. L is a lamp light. This is a lamp light driven system. It means that when you turn the key on, the power goes up through that light bulb and turns the regulator on. If the light bulb's out, the regulator doesn't turn on. so you need to fix the light bulb. I is ignition. That's also meant to be an on command so that the regulator can see that in the event that the light bulb goes out. But most of these didn't have 2 wires anyway. And secondly, sometimes that would be an intermittent problem because it didn't always identify the ignition as the on command. And then S is your sense wire, which was basically told the regulator what the alternator was putting out. Most of these, again, only had like 1 if 2 wires in them. Most of them only had the lamp light. A few of them had 2 wires going to it, the L and the I, and like I said, the Corvette had all 4. But this is kind of how this system worked. You turn the key on, power travels through the light bulb and down the regulator. So the regulator's looking at this wire. What do you think voltage is going to see on that wire? Because that light bulb has not had the circuit completed, there's no amperage flowing, so the resistance isn't going to show a difference in voltage. Voltage is the pressure that's going through that line. There's nothing resisting it because it's not grounded. So it's going to see voltage go straight through that light bulb wire and straight down the end of that wire. It's going to see system voltage or battery voltage at this point in time. When the regulator sees that battery voltage, it takes the battery voltage from the B plus stud and activates the rotor field because this is a B circuit. Let me explain the difference. A B circuit would be like a light bulb. If your light bulb's grounded all the time and you turn on the switch, what are we sending down the wire to the light bulb? We're sending battery voltage down the wire. The reason I say battery voltage is because if you remember it that way, you'll remember it's B is battery. You're adding battery voltage, B plus, to the wire. And that's how that works as far as a B circuit. An A circuit would be, a good example would be a horn. There's always power at the horn. It's hot all the time. Isn't that going to drain the battery? No, it's not. Yeah, it's not because the circuit's not complete. But that is an A circuit. So it's got power all the time, and I'm introducing a ground. That would be an A circuit. And then the horn honks. This one's a B circuit. So when the regulator sees that 12 volts on that wire, it takes that battery voltage and applies it to the field rotor, B circuit. It adds battery voltage to the rotor. Before you start the car up, it will look at one leg of the stator and see that it's not charging, and it'll ground that wire. And once it grounds that wire, that circuit's completed, that light will come on in the dash. But at that point in time, the bulb's using up most of the voltage, so if you had your voltmeter and you were back probing that wire right there, that voltage would drop down to about a half of a volt to a volt. If it's higher than that, if you see 2 volts there, then you've got a ground problem either with the regulator to the case of the alternator or the alternator ground because it should have used it up. So once you start that vehicle, it will look at this and start charging the car and turn the bulb off. So it's pretty simple to diagnose the lamp circuit ones if you look at this chart. You turn the key on, the bulb should illuminate on the dash. You should see about a volt or less at the actual L terminal. Once you start that thing up, that light should go off, and then you should start seeing charging voltage there because it's sending static voltage through that wire again.